Hi everyone. So in the previous video I talked about the idea that covalent bonds, the electrons are not always equally shared in that bond, that some atoms actually tend to attract the electrons more toward itself than the other atom that's bonded to it. And this is what we call electronegativity, and the result of it is that we have some covalent bonds that are what we call nonpolar because the electrons are equally shared, whereas some covalent bonds are what we call polar because their electrons are not equally shared. And remember, I talked about this trend in electronegativity, which is increasing this way, and we can calculate something called the difference in electronegativity, which is symbolized by delta En here, which is just the difference in the values of electronegativity between the two atoms that are involved in that bond. And if it's a certain value, then you're going to call that bond polar, versus when it's not, we're going to call it nonpolar. So let's look at a covalent bond in this case, which is HF. H has a electronegativity of 2.1. F has an electronegativity value of 4 in that table that I just showed you. So if we take a difference between these two, this is going to be a difference of 1.9. And we can see that 1.9 is pretty close to 2. So this is what we would consider a very polar covalent bond. The way we represent the polarity in the bond is by what we call a vector notation. This is represented as an arrow, where the arrow head goes towards the atom that is more electronegative, so in this case F. And then at the start of the arrow, we put a little plus sign to indicate that that's the more electropositive or the less electronegative side. Another way to represent this is by this delta positive, delta negative symbol. So the side that's more electronegative is given the delta negative symbol, vice versa, the side that's less electronegative given the delta positive symbol. But this bond vector symbol, also called a bond dipole because there are two poles, there's the positive pole and negative pole, is the common way we represent polar bonds in a molecule. So if we were to calculate charge distribution in an HF molecule, we'll see that the H side is blue, which is a positive, and the oxygen side is red, which is a negative. What's important for us is actually molecular polarity. Now, if you look at a molecule like HF, there's only one bond, and because the HF bond is polar, the entire molecule of HF is also polar. But what happens with molecule with many bonds, right? So how do we determine molecular polarity that way? If we have more than one bond, then each of the bond vector will be represented by that arrow symbolism that I just showed you, and each of that arrow has a magnitude, which is just proportional to the delta En component, the difference in electronegativity, and is represented by the length of the arrow. But you can see also that there's their directionality. So if you have multiple bonds, you can imagine one might be going this way, another one might be going that way, another one might be going this way, and so on. Each bond vector then has a magnitude, which is proportional to delta En, but also has a direction. When you want to know whether the molecule is polar or not, so you have to add all of these bond vectors, and the sum of the bond vectors tell you what the value of the overall polarity of the entire molecule. The sum is what we call the dipole moment of that molecule. Now, how do you add vectors? This is not something you need to know in this class, but it's useful to see it so that you can understand why we say some molecules are polar and some molecules are nonpolar. When you try to add a vector, you have to do it this way. Let's say you have a molecule. Here's your central atom located at this position, and then you have a terminal atom that's located here, and there is this atom is more electronegative than that one, so there's a bond vector going this way. And then there's another atom is located here, and because there's a bigger difference in electronegativity, that bond is illustrated as a longer bond vector. This atom is more electronegative than the central atom. So as a result, you have these two vectors, and what you have to do is add these two vectors together to get you an overall vector. The way you do it in vector math, take one of these vectors and you try to put them at the end of the first vector. So you can take B and kind of take it and move it over here so that the start of B is exactly where A ends. Okay, so then it becomes this and that. And then the vector that's a result of adding these two is the one that's illustrated by this dashed line right here. Now, the other way you can add the vectors is obviously you can have B and then you move A all the way up here so that the start of A is exactly where B ends. But you can see that that gives you exactly the the same resulting vector. So this dashed line vector is what we call the resulting vector, which is the result of adding vector A plus vector B. Let's talk about molecular polarity. So here at the top I'm showing you several molecules here, H2O, CF4, CHF3. As you can see, for something like H2O, the oxygen atom is more electronegative than the hydrogen atom. The bond vector goes this way. So when you add these two vectors together using the rules that you just learned for vector addition, you get an overall dipole for the molecule. That's called a dipole moment. It has a symbol mu, and it should have a little arrow at the top because it's a vector quantity. How do we determine molecular polarity? Whenever that mu vector is 0, then the molecule is nonpolar. When you get a mu that's bigger than 0, then we consider the molecule to be polar. Now in this case, when you do add the vectors in water, this vector and that vector, the mu is not 0. So as a result, water is polar. Okay, the mu is actually 1.85 in a unit called the Debye unit. You don't need to worry about it at this point, but that's what it is. If you look at something like CF3H, you can see here that the C and the F is more electronegative, so then there's a bond vector this way, bond vector this way, bond vector that way. The H and the C, it's non-polar bond, so really that part of it we don't care. It's just these three. When you add them together, you don't get a 0 mu, so as a result, this molecule is also polar. What about CF4? If you get another vector going up that way, so you get one vector, two vectors, three vectors, four vectors, and when you add them all together, it turns out that all of these vectors cancel each other out, and your mu is actually 0. So if your mu is 0, that means this molecule is nonpolar. You can calculate mu if you know how to add vectors, but in this class, you're not expected to know how to add vectors. So what I'm going to do is give you some simple rules that you can use to help you predict molecular polarity. The first rule says that if you have molecules where there is no lone pair at all around the central atom and all the terminal atoms are identical, then that molecule is nonpolar. So an example of this type of molecule is the one that we just talked about, which is CF4. It's no lone pair around C, the central atom. All the terminal atoms are all fluorine, so they're all identical. So this molecule is nonpolar. If you add the vectors, you'll get a mu of 0. Second rule, if you have the square planar or the linear shape, either one of those things, from your VSEPR prediction, and you have identical terminal atoms, these molecules are going to be nonpolar as well. And we'll do a couple of examples to show you this type of situations. And lastly, if it's not either one of these two, then there's going to be polar. That's all we're going to use in this class right now. So if you're asked to predict molecular polarity, what you have to do first is draw the Lewis structures. So you want to predict what molecular structure is for the molecule or the ion using VSEPR theories. And then lastly, you can use that molecular polarity rules that I just talked about in the previous slide to help you determine whether a molecule is polar or non-polar, whether it has a dipole moment or not. And as far as molecular shape, if you forget them, you can remind yourself here. You can pause the video and again look back at this. Let's work through an example of using the polarity rules to help you predict molecular polarity. So we have 4 different molecules here. So we'll start with SeO3. And again, the first step is just to figure out the number of valence electrons because you have to draw Lewis structure. So Se is in group 6, so there's 6 electrons there, plus all the oxygens. There's 3 oxygens, each of them has 6, so a total of 24 electrons. Se in this case is our central atom, so then you have 3 oxygens bonded to it. Remember, oxygen has to satisfy the octet rule, so I'm going to start with something that looks like this. 4 times 3, 12 pairs total. That actually is 24 electrons. So I've used up all my electrons, but clearly it's not correct because the selenium in this case is still not octet yet. It has to have at least an octet. So that might be an option for you to draw. That's one drawing that would make sense. It's also possible for me to draw something that looks like this. Even though in this case you have 10 electrons around selenium. So selenium is on the 4th period in the periodic table. So it has the ability to accommodate more than 8 electrons, as we said before. Whenever you get into this type of situation, these are what we call non-equivalent resonance structures. And this is the time when you should use that formal charge rule to help you pick out the best structure. I'm going to just draw one more non-equivalent resonance structure which has all double bonds in this case, okay? And then what we're going to do is show which which one is the most likely structure in this case? We already know that this one doesn't work, so you have to do some calculation of formal charge. I'm going to do this really quickly because I assume you already know how to do this from prior lessons. Remember, selenium is 6, so -4 in this case is a +2. Okay, this one is a -1, this one is a -1, this one is 0. So we want formal charge to be as close to 0 as possible. We really don't want them to be higher than that. So let's see if we can do better than that. We go to this one, we notice that the oxygen here has formal charge of 0. The formal charge of this oxygen is also 0. Formal charge of the selenium now drops down to +1, which is good. This one is -1. We've knocked out this formal charge, but we still have 2 atoms that have formal charges. See if we can do better. We go to structure number 3. Now all the oxygens are 0, and the selenium is also 0 because it's 6 minus 6. So now we have a great structure because all the formal charges are 0. So this is the one that we're going to use to predict our molecular polarity. So your selenium is your central atom. These are double bonds, but they count as one effective pair for VSEPR purposes. So we got 1, 2, and 3. They're all bonding pairs. So there's 3 bonding pairs, which means the molecular geometry in this case is trigonal planar. Okay. Now the last thing to do is to then look up that molecular polarity rule and see what this molecule should be, whether it's polar or non-polar. Because there is no lone pair and all the terminal atoms are identical, this fits the rule that's highlighted there. So without going any further, I would say this SeO3 molecule is nonpolar. Or another way to say is it has no dipole moment. There's 0 dipole moment. I'm going to pick PCl3 now as my second example. So we're going to start with lowest structure. P is in the middle. Cl, Cl, Cl. I'm going to put that pair right in the middle. Okay. Could have drawn something like this as well. Okay. Right. And adding more and more double bond, just like I did in the earlier structure. The question is, should I or not? To help you answer that question, you have to look at the actual formal charges of each of the atoms and see if when you move from this structure to that structure, you improve the formal charge situation. The reason we look at formal charge in this case is because these atoms can violate the octet rule. So we use formal charge as a guide as far as whether we should draw one way or the other. If you look at the calculation of formal charges here, chlorine and the phosphorus, they all have 0 formal charges. If you go to this one, you notice that the phosphorus here is +1. This particular chlorine is -1, and everything else is 0. I can draw it a different way, but either way, you're going from something that has 0 throughout to something that is not 0 throughout. So you're making the situation worse, so you don't want to draw something like that. So you're sticking with this drawing with all single bonds. Now, once you're satisfied with that, then what you need to do is then go ahead and try to use that to predict your VSEPR structure and then your molecular shape, and then afterwards your molecular polarity. So the VSEPR structure here depends on the central atom. So you have how many bonds, how many pairs of electrons, 1, 2, 3, and don't forget this one right here, 4. 3 bonding pairs and 1 lone pair. The tetrahedral electron geometry, but it's only 3 of them are bonding, so we call that trigonal pyramidal, whether it's polar or non-polar. Again, we have to go through the molecular polarity rules that I talked about at the beginning of this video. If you look here, you have identical atoms, but not all of the electron pairs are bonding pairs. So one of them is lone pair, the other 3 are bonding pairs, which means that we have lone pairs and polar bonds, but not square planar or linear, so the molecule is polar. Alright, so I hope these examples shows you how to use those molecular polarity rules that I just mentioned here in combination with VSEPR and Lewis structures to predict molecular polarity.